Hello, this is the solution of worksheet 2.5 and 2.6. So we'll start with the MCQ questions. Number one, find the constant a and b such that the function is continuous everywhere. Here is piecewise defined function, yani defined by region. In each region, of course, the function is continuous. But when we take apart from each one and put them together, we may have discontinuity at the point where we join the two parts. Okay, so here we will check the continuity at -1, x equal to -1. So this is MCQ 1. At x equal to -1, since we have two expressions depending on -1 plus or minus, then we will take the limit to the right and limit to the left. X approaches -1 plus, and f of x in this region, -1 plus, is defined by the second one here. Okay, so I will take ax plus b. So if I replace here, it will give -a plus b. Okay, on the other side, limit x approaches -1 minus, and the expression for -1 minus is given by the first one here. So it is limit of 2, so it is equal to 2. Since we want to have the continuity everywhere, so these two must be equal, okay, and equal to, of course, f of -1, which is 2. So this is f of -1. Okay, so I will have the condition that -a plus b must be equal to 2. Okay, I will call this condition number 1. And then we continue to check the continuity at the point 3. X equal to 3. I will do the same thing. So limit to the right of f of x. And when we say right of 3 plus, that means we are in region number 3. So it is limit of -2, which is equal to -2. Then limit to the left, x approaches 3 minus. The expression 3 to the left is given by ax plus b. So we substitute here x by 3. It will give 3a plus b. And we need to make these two limits equal. And of course, here the -2 is the value of f at the point 3. So the continuity is guaranteed when we take the equality between 3a plus b and -2. So for that, I will write the second condition, which is 3a, I must have 3a plus b equal to -2. And I will call this second condition. So now, put 1 and 2 together and solve these two equations for a and b and find their values. So if I do this, then clearly I can, from 1, conclude that b is somehow a plus 2. I can write it like that. And when I will use 2, then I will substitute b by a plus 2. So 3a plus a plus 2 equal to -2. Then this gives 4a equal to -4. That means a equal to -1. And if a equal to -1, this gives also b, because b is a plus 2. So b is equal to 1. And the answer here is, of course, the C. Okay, now we move to the second MCQ. Okay, so number 2, we want to compute the limit of this function when x approaches minus infinity. So first thing, we will, if we substitute, of course, this will give indeterminate form. So I will try to change the expression a little bit. So I will put inside the square root, I will put x squared common factor. So factor 1 plus 1 over x plus 6 over x squared. So all this inside the square root. Clearly, this quantity will go to 0 as x go to minus infinity, and this one is also going to 0. So it's like between the parentheses, all this will go to 1. So all this quantity will go to 1 when x approaches minus infinity. So 1 times x squared, if x is going to minus infinity, x squared is going to plus infinity, and the square root of plus infinity is still plus infinity. So the answer here is the limit is equal to infinity. And the answer is B. Now for the third MCQ, MCQ number 3, find the horizontal asymptote of the graph of this function. So as we said, for the horizontal, we need to compute the limit x approaches plus or minus infinity. So let's start with limit f of x when x approaches infinity. So this will give limit. If we substitute, then I will get infinity over infinity. So this is indeterminate form. So I have to change a little bit the expression, and I will put x squared in common factor in the numerator. So for common factor 2 plus 2 over x plus 3 over x squared. Over same since the highest monomial is x squared, so I will put also x squared common factor 4 minus 4 over x, and again we apply the limit when x approaches infinity, so this will go to 0. This also same thing, and this one will go to 0 as well. So this will cancel with this, and finally I will find 2 over 4, that means half. And by the way, this is also available for x approaches minus infinity. So the same result will be for minus infinity. So I conclude that y equal to half is a horizontal asymptote. Okay. So the answer here is B. Now move to MCQ number 4. And we have 3 statements. We want to see which of the following are true or is true. So let's start with the first one. Limit of f of x when x approaches 3 is equal to minus 1, giving the information that limit of f of x, x approach 3 minus is minus 1. Limit to the right also is equal to minus 1. So yes, statement number 1 is true. Second one, f is continuous everywhere except at x equal 3. We don't know this information, so this is wrong. In general, we don't know. The question is not giving any information about the continuity outside of 3. Number 3, f has removable discontinuity. Yes, this is true because limit to the right is equal to limit to the left. Okay, and 3 plus is equal to limit f 3 minus, so the limit exists. Well, we don't care about if it is here, of course, this is discontinuity because f3 is not defined, but the limit exists. So it is a removable discontinuity. So 1 and 3 are true, only 1 and 3. So the answer is C. Now we will move to the essay question. Essay part. And for the first one, we want to explain why the following function is discontinuous at the given point. So for A, remember that the continuity is guaranteed when we have three, let's say one condition, which is limit f of x when x approaches a is equal to f of a. And I said maybe two conditions because this limit when x approaches a, we can divide it in two limits, a plus and a minus. They should be equal to make sense to this limit. Okay, like the case here for number a. So the expression is the same here for the point 1 plus and 1 minus. So my limit will be when x approaches 1 is the limit of x squared minus x over x squared minus 1. So clearly when we substitute, this is 0 over 0, so indeterminate form. So I have to continue, limit x approaches 1, x multiplied by x minus 1, and x minus 1 multiplied by x plus 1 when we factor all this. So we simplify by x minus 1, and then we can substitute, so it is equal to half. Okay. Is it equal to f of 1? No, because f of 1 is equal to 1. So this is not equal to 1. So it is a discontinuity. And the type of discontinuity here is removable discontinuity. Okay, number B. Here, the target is to study the discontinuity at 0. So, and in this question, I need to specify 0 plus and 0 minus because the expression is not the same. It's not like the example A, where we have the same expression for 1 plus and 1 minus. But here, we have to differentiate the cases. So x approaches 0 plus. 0 plus, that means I am in the region number 3. So I will take 1 minus x squared. Okay, this limit. And when I substitute, it will be equal to 1. Now limit when x approaches 0 minus. 0 minus is the first region, so it is cosine x. And limit of cosine x when x approaches 0 minus, it's cosine 0, and cosine 0 is equal to 1. Okay, so limit to the right is equal to limit to the left, but so I can conclude here that the limit of f of x when x approaches 0 is equal to 1, but it is different than f of 0, which is equal to 0. So this is discontinuity, and it is removable discontinuity. Now we move to question 2, and here I will configure. I will work directly on the worksheet. So you see here from the graph, we state the following, the points of discontinuity of f. So clearly, there is discontinuity at x equal to minus 2. Okay, so this is the first one. there is discontinuity at x equal to 2, x equal to 4, x equal to 6, and of course, the last one where we don't have continuity is x equal to 8. So here, the discontinuity x equal to -2, this is a jump, of course. Let me write here, x equal to -2, this is a jump. X equal to 2, also jump. Let me put the jump together. So x equal to 6, jump. Okay. And x equal to 4. I hope I didn't miss anything in the continuity. X equal to 4. This is infinite discontinuity. Of course, x equal to 8, this is the end point. So it is not included in the continuity because it's the last part, the last point in the interval, in the domain of definition. So we can make it open. It is discontinuous there, but we don't have the type. Okay, now for the intervals, intervals of discontinuity. So here the intervals we have to keep attention to the fact that we will consider each interval by itself, not the whole domain. Okay, so interval by interval, we will see the continuity here. Okay, so question B. The first interval, since it is closed, -4 till -2 open. The second one, so let me remove this writing here. Two, two, open, and then close it. Two, 4 open, then 4 open, 6 open, and the last one 6 to 8 open. These are the intervals where the function is continuous. So as I said, we take interval by interval. So if you have closed, you put it closed, open, you put open. We don't consider the whole domain. This is another story to take the domain of continuity, because we need to pay attention to the discontinuous part. Okay, question 3. We need to show that this function has a root in the interval -1, 2. So this is we are called the IVT here. Question 3a. The function p of x is continuous everywhere on all. So in particular, on the given interval, which is -1, 2. This is the first condition, continuity. And then we need to compute p of -1 and p of 2. One of them is positive, the other is negative, so we can conclude. P of minus 1 is equal to 5, 5 minus 5 minus 10 plus 5. So it is equal to minus 5. This is negative. And P of 2, 2 power 4, that's 16 times 5, that means 80, minus 4 times 5, 20, and plus again 20 plus 5. So this gives 85, which is positive. So one is negative, one is positive. The IVT with continuity, we apply the IVT. There exists at least one root T, which belongs to the open minus 1, 2, such that P of T is equal to 0. Okay. And now we will see in example B that the IVT cannot be applied because one of the conditions is not satisfied. So if we see here the B, why we cannot apply the IVT? Because g of x equal to 1 over x over the interval minus 1, 1. Although we have g of minus 1 is equal to minus 1, this is negative. G of 1 is equal to 1, this is positive, but we cannot conclude with the IVT because g is not continuous on the interval minus 1, 1. And more exactly, g is not here, not continuous. He is not continuous at the point 0. The problem is at 0. It's not even defined at 0. So we cannot apply the IVT. Okay, let's move to question number 4. So again, here it's an application of IVT, but you see here that for question 4, the interval is not given. So it's our duty to find the good interval here. In question 4, we want to prove that f of x equal to x minus cosine x has at least 1, 0. So we will guess the interval where we will work. So I will try to take, by the way, f is continuous everywhere. It's continuous on R, whatever the interval, because it's x function and cosine function, difference of them is continuous everywhere. So I will choose, I will try to work with the interval 0 and maybe let's say 0 and 1 maybe. 0 and 1. And by the way, the function inside, the variable inside the trigonometric function are all the time in radian. So if you use calculator, put the radian mod. Okay, so f of 0 is equal to 0 minus cosine of 0. Cosine of 0 is 1, so this is equal to minus 1. But f of 1 is equal to 1 minus cosine 1. For sure, this is positive because cosine of anything is less than 1. So we can use calculator and confirm that this is positive. So the IVT will give me that there exists C in the interval 0, 1 such that C minus cosine C is equal to 0. That means root for the function f. Now we will move to the question 5. For the horizontal asymptotes, we need to compute in general the limit at infinity and minus infinity. But here we will need we can do both plus infinity and minus infinity at the same time. So I will compute the limit of f of x when x approaches infinity. So I will have x squared minus 5x plus 6 over x squared minus 4x plus 3. In fact, this is indeterminate form, so I need to remove this indetermination by taking common factor x squared in the numerator, okay, plus 6 over x squared. So here, all the time, if you want to verify, just expand and you will find the previous expression. Do the same thing for the denominator. So 1 minus 4 over x plus 3 over x squared. So clearly here we have this going to 0, this going to 0. Same for this, all these going to 0. Okay, so I will have this cancellation also. So 1 over 1, so the limit is equal to 1. And I can conclude that y equal to 1 will be horizontal asymptote. Normally, we need to compute also limit at x approaches minus infinity. But here the computation is the same, so the limit is equal to 1. So my conclusion is that y equal to 1 is horizontal asymptote. That's the only horizontal asymptote here. So y equal to 1 is a horizontal asymptote. So we can go to the question number 6, and here we will evaluate the limit Okay, so here question 6. As usual, this limit I will make the common factor for the dominant term. So x factor 2 minus 1 over x. And I will do the same thing inside the square root. So x squared factor 3 plus 1 over x plus 6 over x squared. So as usual, all this inverse of power of x will go to 0. This will go to 0. And this will go to 0. Now I will have this root of x squared. Root of x squared is in general absolute value of x. But since here I am working with minus infinity, so this will be equal to, because x is negative, so this is like minus x. So my limit will give equal limit of x over minus x. So the limit will be equal to minus 2 over root 3. If it was at the plus infinity, then I will find plus. So we can conclude here that y equal to minus 2 over 3 is horizontal asymptote. Y equal to minus 2 over root 3 is horizontal asymptote. Okay, question number 7. This is computation of limits. So I will compute them quickly. So I have to compute limit cosine x multiplied by exponential minus x. Remember that cosine by itself does not have limit at plus or minus infinity. But when we multiply this by a constant function, we can think about the squeeze theorem. So I will bound cosine x between its range bounds 1 and minus 1. then I have that exponential minus x is all the time positive, this one. So I can multiply by exponential x, then it will give minus exponential minus x less than exponential minus x cosine x and less than exponential minus x. So I took this equality and I multiplied by exponential minus x, which is positive. Okay, so this will give the limit of this one. Remember, when x approaches zero, sorry, approaches minus infinity or plus infinity here, then exponential minus x will go to zero. So this will go to zero, and this one also will go to zero by the squeeze theorem. It will give me that the limit of this function cosine x times exponential minus x when x approaches infinity is equal to 0. And this is the last conclusion. Okay, now I will go to the question B. This is A, by the way. And for B, I will compute the limit at infinity. So I will do the same strategy of factoring the dominant term. X approaches infinity. So I will put exponential x as common factor in the denominator, numerator, and in the denominator. So it's 1 over exponential x here minus 1. Okay, over same thing, exponential x, 1 over exponential x plus 2. And remember that when x approaches infinity, then exponential x approaches infinity also. This gives that 1 over exponential x approaches 0. So all this will go to 0. And this one will go to 0. This will cancel with this. So my limit will be equal to minus 1 over 2. Okay. And the last question here, question C. We want to compute limit exponential tan x when x approaches pi over 2 plus. X approaches pi over 2 plus. So tan x approaches, and let me recall you what happens for the tan is something like that, So this is pi over 2, and pi over 2 plus, we are going to minus infinity. So this is minus infinity. Then I will take exponential tan x will approach exponential minus infinity. That means 0. So the limit when x approaches pi over 2 plus of exponential tan x is equal to 0. And by that, we finished this worksheet. Thank you so much.